Okay, so this is section 4.3 on logarithmic functions. And oftentimes this is a tough topic, so the good news is you have a video. You can stop it whenever you need, replay it if you need to, in order to get this idea if it's not one with which you are familiar. We're going to start off the idea with the idea of an inverse function. So inverse functions, if you remember, undo each other. So addition and subtraction, like add 5 and subtract 5, undo each other. Multiplication and division, multiply by 10, divide by 10. Squaring and square rooting, as long as you only use positive values of x. If you square 5 and then you square root it, you'll get back to 5. So that was a concept we talked about for the first test. Well, it turns out that logarithmic functions and exponential functions do the exact same thing. If you put an exponential into a log, it will undo it if you have the same base, and vice versa. So that's what we're going to get to. That's what we're building to. But we're talking right now about just defining what a logarithmic function is. The base of a logarithmic function is going to be a lot like the base of the exponential. So we talked about a base a in exponential having to be positive but not equal to 1. Same thing's going to be true for our logarithmic function. A is going to have to be a positive number but not equal to 1. And in this case, our x values that we're going to use, so the domain of our logarithmic function has to be greater than 0. So if you remember when we talked about inverse functions, the domain of one function was the range of the inverse and vice versa. So we know our exponential functions that we just talked about have a range where y is greater than 0. Negative numbers don't come out of our exponential function unless we flipped it over with a negative sign. But if we think about our exponential function that we talked about, the range was greater than 0 for y values. So that's what our domain is going to be for our logarithmic function. We're only going to use x values greater than 0. And so this new function that we're talking about, y equals the log base a of x. So this is called the base. This is called the argument. So if we use a base of a and an argument of x, and that equals y, it means the exact same thing as if you take that base a and you raise it to the power y, the answer should be x. So when you say log y equals the log base a of x, the other way you can think about this is that a is the base still, so that's not new. A is the base. Your exponent is what's on the other side. So y would become the exponent in the exponential. And x, which is called the argument, is going to be the answer. So it has the same first letter, answer. The answer, or the argument of the log function, is going to be on the left-hand side of your exponential, and what's on the left-hand side of your log function is going to become your exponent. They mean the exact same thing. Or if we start with the exponential function like we did last time, y equals a to the x, that means that x, which is your answer, is going to be equal to the log with this base of y. So the log base a of y will equal x. So you can either start with the exponential to write the log or start with the log to write the exponential. You just want to practice that a little bit. But let's just look at an example with an exponential. Like if I said that I want you to take 2 and raise it to the third power and you get 8. saying 2 to the third power is 8 is the exact same thing as saying that 3, the exponent, 3 equals the log base 2 of 8. These are the exact same statement, one written as an exponential and one written as a log. The log base 2 of 8 is 3, means 2 to the third power is 8. So the domain of our exponential, back to that picture I had a minute ago, the domain of our exponential being all real numbers, any value of x can go in, means that's the range of our log. Any real number can come out of the log. The range of our exponential being only positive numbers, or not even 0, only positive numbers, means the domain of our log A is only positive numbers. So inverse functions switch their domain and their range. And if you remember, inverse functions flip on the line y equals x. So since I know what the graph of y equals a to the x is, I should be able to figure out what the graph of the log is. And that would mean that this point here, 0, 1, would flip here to 1, 0. We're going to switch our x and our y. And our log function is going to look something like this. And that means that I'm only going to put positive values into it. The domain is only positive values. But all different y values can come out of it. The range is all values from negative infinity to positive infinity. Remember, range, you sort of turn your head and look at the y-axis. So this is our new function that we're going to be using. And there's some properties of it. If we ask for the log base a of 1, the answer is going to be 0. And the reason is, if you write this as an exponential, it's the base to this exponent equals that answer. A to the 0 equals 1. And because a to the 0 equals 1, the log base a of 1 is 0. Anything other than 0 to the 0 power is 1. But we've already said that a is not allowed to be 0. So this is a property we can use. The log base a of a is equal to 1 because a to the first equals a. Base to the exponent equals answer. So if you ever see the log base 6 of 6, that's 1. The log base 8 of 8, that's 1. The log base a of a to the x is x. And the reason is a raised to the x power is a to the x. This is the answer. This is the exponent. This is the base. So we're just using a rewrite to prove to ourselves that the log base a of a to the x is in fact x. And the last property of logarithms we want to know is if the log base a of x equals the log base a of y, so this argument is x and this argument is y, those arguments have to be equal to each other. So using those properties, we can simplify some log statements. Before we get into actually, evaluating or solving for x, we want to practice going back and forth between the logarithmic equation and the exponential. So this is the logarithmic equation. They've said the log base 2 of 1/16 equals -4. Let's just verify that and make sure that's true based on the exponential. So the base 2 to the exponent 4, -4, should equal the answer, which is 1/16. So does 2 raised to the -4 equal 1/16? If it does, then this log statement was true. And 2 to the -4 is 16. So the exponential form is showing that that log statement is true. Does 4, which is the base, raised to 1/2, which is the exponent, equal 2? Yes, it does, because a 1/2 power is a square root. So the exponential form is verifying that log statement is true. Going the other way, the base is 9. So this is a log base 9 statement. The log base 9 of 27 equals 3/2. Because 9 to the 3/2 is 27. So this is the log form of the exponential. Not as easy to verify that's true. We know this is true. So this is also true. And then here, the log base 6 of 1/36 equals -2. This is the exact same statement as that exponential statement. So you just have to get used to using the base for your log, finding the argument on the other side, and finding the answer here in your exponent. So if we're using that idea, this question, the log base 3 of 81, is the same question as what power do I raise 3 to get 81? And the answer to that is 4. 3 to the 4th power is 81. So the log base 3 of 81 is 4. What power do I raise 2 to get 1/8? And the answer is -3. 2 to the -3 power is 1/8. So the question marks here, the answer is -3. What power do I raise 64 to get 4? And the answer is the 1/3 power. You need the cube root to get from 64 to 4. So if you see a fraction as your argument, the answer is going to be negative. If you see your argument is larger than your base, then most likely you're going to have an integer. And if the argument is smaller than your base, then most likely you're going to be using a root or a fractional exponent. And then this one, what power do I raise 12 to get 1? The answer is 0. So that's like this property here, the log base a of 1 is 0. So we can use this going back and forth from logs and exponents to also solve using the properties that we have up here. Don't want to get them off screen. So the log base 5 of 5 is x. Well, we already know that the log base a of a is 1, so that means x has to equal 1. The log base 4 of 4 to the 5th equals x. Well, we have a property here. The log base a of a to the x equals x. So the log base a of a to the x equals x. The log base 4 of 4 to the 5th equals x. That means x has to equal 5. And then finally, the last property, the log base a of x equals the log base a of y, means that x and y are equal. That's what this is saying. The log base 2 of this argument equals the log base 2 of this argument. You can set your arguments equal to each other and solve. So the properties are going to be used in your WebAssign to solve equations. And you might know enough about logs that you already know how this base undoes that base. But using the properties can help you practice that as well. So flipping over to the second page, I've already sort of done this. I did a little preview of it. The graphing the 2 to the x and the log base 2 of x in the same plane. So we know that 2 to the x, we've already talked about how to graph that. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. 2 to the 3rd is 8. So we got that general idea of the exponential heading up. And then on the flip side, getting closer and closer to 0, because as we use negative exponents on 2, that becomes closer and closer to 0. And we know that the log function should flip across the line y equals x, since it's the inverse function. So the point 0, 1 becomes the point 1, 0. The point 2, 2, the point 1, 2 becomes the point 2, 1. So these two are flipping. The point 2, 4 becomes the point 4, 2. And finally, the point 3, 8 becomes the point 8, 3. So this part of the exponential will flip along the line y equals x, or reflect along it. And then this part will start heading down to the y-axis, just like this part approached the x-axis. So this is the graph of y equals 2 to the x, and this is the graph of y equals the log base 2 of x. They're reflections of each other. And we can move those, transform this log function just like we did any other function. By adding 3, we can move it up 3. That's adding 3 outside of the log, outside of the function. If we decide to add 3 inside the function, that would be in the argument of the function, and that would move it to the left 3 units. If we put a negative in front of it, it'll reflect it over the x-axis. And if we put a negative inside the function, that's in the argument, it'll reflect it over the y-axis. So reflecting over the x-axis would take it from here and would make it flip over, and it would do that same thing flipped over the x. Flipping over the y-axis, if it did this, it would now do this. So that would be flipping over, reflecting over the y-axis. So all of those rules for moving functions work with the log as well. There's a very special base. We use the base 2 here. On the flip side, we used all different kinds of bases, but there's a special number that's called e. And it's an irrational number. It's on your calculator. It's approximately 2.7. Just like pi is approximately 3.14. You can't actually write out exactly what it is because it's irrational, and it will never terminate or repeat as a decimal. But if you just imagine it somewhere around 2.7, the natural log has its own expression. It's ln. But what it really means is use the log and use e as the base. So log base e of x and ln of x are interchangeable. You can use either notation for me. I really don't care, but you do need to know if it's given as ln of x that they're just talking about the log base e. And all the properties that we just had work for ln just as they do for log base e, because they're both logs. So if you're trying to evaluate the ln of 1 over e, what you're saying is you want to know what exponent you raise e to turn it into 1 over e. Base, exponent, answer. So e to what power becomes 1 over e? And the answer to the question is -1. So we're just imagining trying to use our exponential to figure out our answer to our log. This is very different than the ln of 1/3. That's not what this means. This means 1/3 times the ln of 1. Because 3 is not in the argument of the log, I have to think of the ln of 1 as one quantity. But the properties of log says the ln of 1 or the log base 5 of 1 or the log base 10 of 1, they're all 0. So this is 0 divided by 3. The answer is 0. And then this says 2 times the ln of e cubed. So the ln of e cubed is, there's another property there. It's saying the log base e of e cubed. So if you look back on the property sheet, it's like this, where it's the log base a of a to the x is x. The ln of e to the third is 3. Because the question is, what power do you raise e to get e to the third? The answer is 3. So 2 times, oops, sorry, I'm not showing that to you. Sorry about that. There we go. The ln of e to the third is like the log base e of e to the third. What power do you raise e to get e to the third? It's 3. So this part is 3, and then you're multiplying it by 2, and you're getting 6. If you want to write the ln as an exponential function, the only thing you have to remember is the base is e. So as an exponential, this means e to the 0 equals 1. As an exponential, this means e to the negative 1 equals 1 over e. So this is just verification that this log statement is true. If you want to write this log function as, or write this exponential as a log function, e being the base means it's an ln. So you would want to rewrite it as the ln of 4 equals x. Or you could write it as the log base e of 4 equals x. It's the same thing. And this would be the ln of 2 equals the opposite of x. Log base e of 2 equals negative x. So back and forth between exponential and log. You just want to practice that until it becomes automatic. And then the last properties of logs from the previous page. If the bases are the same, the arguments have to be the same. Well, if it's ln, they both have the same base of e. So you just say x minus 4 equals 2. Because the arguments have to be the same, x would have to be 6. And here you'd have x squared minus 2 equals 20.